We are told that the battery has an unknown internal resistance, but that just means that we cannot just ignore the internal resistance. The switch is initially open, and that switch is closed. The voltmeter is connected. It reads 9 volts. That's an EMF. If there's no current flowing, as it is because that switch is open, then it's going to read 9 volts. Now I close that switch, and when I close that switch, I actually land up with it turning into 6 volts. So now we've got an external voltage of 6 volts, and we need to keep that in mind. That means that my lost volts would have been equal to 9 minus 6, which is equal to 3 volts. Determine the total resistance of the external circuit when both switches would be closed. So it's 1 over R parallel is equal to 1 over 6 plus 1 over 3. When I rearrange that, I'm going to get that is equal to 3 over 6, and therefore R parallel is equal to 6 over 3, which is equal to 2 ohms. The external is therefore equal to 2 plus this 1 over here, which is equal to 3 ohms. Calculate the current in the ammeter when both switches are closed. Now, when both switches are closed, I've got this voltmeter reading over here, the 6 volts. So I'm going to say that the series current is equal to, and I need to link things together, the voltage external, and therefore I have to use the resistance external. And that turns out to be 6 divided by 3, and I land up with 2 amps on the ammeter. Determine the internal resistance of the battery. Now, R internal is equal to lost volts divided by series current, and that is going to be equal to 3 volts divided by the series current of 2, and I land up with 1,5 ohms of internal resistance. How would the readings on the ammeter and the voltmeter change if I opened switch 2? Now, opening switch 2 means that I get rid of this whole branch. What I am therefore doing is I am increasing the resistance of the entire circuit. So I'm going to decrease the current strength. So the ammeter decreases. Why? Because the external resistance increases. Or if you even prefer, the total resistance increases, because I have removed a parallel resistor. And then they ask me what is going to happen to V2. V2, that increased resistance is going to require more energy to be able to get through, because I have got more energy required to go through the 3 ohm resistor. Now, if I wanted to, I could actually have done a calculation to prove that, and we don't know this current any longer, but let's just do a side calculation over here. We know now that my new total resistance is going to be equal to 3 plus 1 plus what was my 1,5. So I've gone and I've added all of those up. Because my resistances stay the same no matter what has happened, the actual values of each resistor. So I land up with 5,5 ohms. Simultaneously, I know that my EMF is unchanged. So I can get a new series current by using the EMF divided by the total resistance. And that is equal to 9 divided by 5,5. And I land up with 1,64 amps. Now if I want to work out this voltmeter over here, V is equal to I times R. My new resistance, at least my new current is 1,64. My resistance is 3. And I land up with 4,9 volts. Now, what was the reading on that voltmeter before? Before the whole thing happened, we landed up with that voltmeter would have read the current, which was 2 amps, multiplied by the resistance of the parallel network only, which was 2, and that's equal to 4 volts. So 4 volts has now gone to being 4,9 volts, and that is an increase. So I can actually show it by calculation, but it is logical that it is going to require more energy to go through the more difficult resistance. Got the following diagram. Internal resistances are negligible. EMF of the battery is 24. Internal resistance you can't ignore. When the switch is closed, we've got 2 amps and 1,5 amps. So let's put that on. 2 over there and 1,5 over there. If my main branch has got 2, everyone agree that I would have 0,5 amps going along through there. Calculate the total resistance of the circuit. So it's again 1 over R parallel is equal to 1 over 30 plus 1 over 10. Oh dear, I don't have enough information. I don't have that resistor. But I do know the total EMF and I know the total current. So I am going to do something very simple, and I am going to say the total resistance is equal to the EMF divided by the series current. And that is going to be equal to 24 divided by 2, which is equal to 12 ohms. Easy. Determine the resistance of R3 if the reading on V1 is 7. So I've got 7 volts over here, and now we want to know what that resistance value is. R3 is equal to the potential difference across R3 divided by the current going through R3. I have both of those pieces of information, so it's going to be 3,5 ohms. What is the reading on V2? Well, I have got a parallel resistance, which I was busy working out a few seconds ago. And, oh no, I've been given even more better information than that. I've got 1,5 times by 10, because I'm just looking at the bottom branch. V2 is equal to 10 multiplied by 1,5, which is I times R, and for that particular resistor, and I land up with 15 volts. So what that leaves me with is, if I've got 15 volts down here, 7 volts over there, that means my lost volts is equal to 24 minus 15 minus 7, which is equal to 2 volts. So that's my lost volts, and therefore if I want my internal resistance is going to be lost volts divided by series current, and that is going to be 2 divided by, my series current is 2, and I land up with 1 ohm. What is the power dissipated in R3? Power is equal to V times I. I can use 7 times the current of 2, and I land up with 14 watts. And then finally determine the work done in moving a charge through the 30 ohm resistor. Work done is energy transferred, and it's moving a unit charge through there. So the work done in moving 1 unit charge is actually called potential difference. So the potential difference over the 30 ohm resistor is going to be exactly the same as over the 10 ohm resistor, and so it is going to be 15 volts as well. Taking a look at my next example, the EMF of the battery below is 9. The internal resistance is given. An ammeter and 4 resistors are connected, and the resistors have values. Calculate the total resistance of the circuit. They've given me the values of all of the resistors, so I can say 1 over R parallel is equal to 1 over 3 plus 1 over 1. That's the parallel network down there. And therefore R parallel, when I invert it and everything, turns out to be 0,75. And then my total resistance is going to be equal to 7 plus 12 plus 0,75 plus 0,25. And that works out to be 20 ohms altogether. Calculate the reading on the ammeter. I is equal to V over R. I know the EMF is 9. I know that the total resistance is 20, and therefore I get 0,45 amps. They then say what is the reading on the voltmeter, and the voltmeter is only over the parallel network. So I've got 0,45 coming along over here. The parallel network has been reduced to a 0,75 ohm single resistor equivalence, and therefore I can say the potential difference across the parallel network is the current going through the parallel network, which is 0.45 in total, and the resistance of the parallel network is equivalently 0.75, and so I get 0.3375 volts.